Hello, my name is Mark Trulot, and this video is to help you get started with Frame. What I will be showing is how to quickly and easily structure an object-oriented class as a state machine, or more accurately, an automaton, using Frame notation. Frame is a highly opinionated textual markdown language that can generate object-oriented classes called controllers, as well as the corresponding UML documentation. And at the time of this recording, Frame generates controllers in 6 object-oriented languages, with many more to come. Let's start by taking a look at how Frame organizes a class. Frame specs consist of up to 4 internal sections, or blocks. It is not required to have any, but if they do exist, they must come in a specific order. It is perfectly valid to have no blocks in a Frame spec, which simply results in an object-oriented class with nothing in it, so not very useful. One of the key aspects to the Frame pattern for implementing state machines is the Frame event. Frame events are simple objects that contain 3 essential data members: a message, a parameter dictionary, and a return object. Frame uses frame events to decouple the internal system blocks from each other, and yet enable them to work together in a standardized way. The first section is the interface block, where the public API is defined. Interface methods have one job: to send a frame event object to the internal state machine. The interface method initializes the frame event with data from the interface call, and then sends it to the state machine block. After processing, if a result comes back on the frame event, then that will be returned to the caller. The example we will develop here is for a binary system containing a 0 state and a 1 state. However, we will also need a third start state to help initialize the system. States are comprised of 0 or more event handlers, which are triggered by frame event messages to execute behavior. At a high level, behavior consists of 2 kinds of things: actions and transitions. Actions live, not surprisingly, in the actions block. At this time, actions can only be declared in Frame, but not defined. This is due to current limitations in Frame as a programming language. However, using inheritance, it is easy to add the missing functionality in the native target language. We will see how to do so later in this video. Member variables for the class are declared and initialized in the domain block. Both event handlers and states, as well as actions, can access and manipulate them. Now that we have explored the high-level organization of a frame-generated class, let's examine the frame notation that defines it. Here we can see the frame spec for the system we will implement. In orange, we see the interface with 2 interface methods, start and change. As discussed, each of these methods will instantiate a frame event and send it into the state machine. Notice that no parameters or return value are declared. In Frame, if parameters or return values don't exist, or are a default value, they're not specified. In Frame, the @ symbol stands for a frame event, and the pipes indicate the message the frame event is carrying. By default, a frame event message is the same as the interface name that created it. This default behavior can be overridden by the notation you see here. This is known as a message alias. Therefore, the message carried in the frame event for the start message is a token with the 2 greater than symbols, which, in Frame, is a special token meaning start. Next in the specification is the machine block containing 3 states: start, 0, and 1. States are indicated by the $ symbol preceding an identifier. States contain event handlers, which begin with an event handler message selector. Message selectors consist of 2 pipes surrounding a message string. Our start event handler in the start state triggers a transition to the 0 state. State transitions are indicated by the arrow token. Finally, all event handlers are terminated either by a return token or a continue token. The return token is the caret we see here. We will discuss continue tokens in later videos. As we can see in the 0 and 1 states, we are also selecting for a single greater than symbol as well. This token means enter the state. Unlike the start message, the enter message and its corresponding exit message are special and generated as part of the state machine inner workings. The exit message is not shown in this example, but will be discussed in later videos. This machine responds to the change event message by transitioning between 0 and 1 in a never-ending cycle. The actions block contains one action, the log method. As we can see here, parameter declarations in Frame use square brackets, while calling an action or any function uses parentheses. Actions can also declare return types, but if omitted, as is shown here, the equivalent of null or undefined will be assumed and generated by default. Finally, the domain contains the member variables. Variables are declared with the var keyword and must always be initialized. You will notice that the cycle count variable does not have a type declared. Frame also supports type declaration, but permits it to be omitted if the target language does not require it, which will be the case for this demo. This completes our quick overview of the internal architecture of a Frame specification. We will now recreate this spec in Frame's free online development tool called the FramePiler and examine the Python code it generates. We will then demonstrate this code running as a working program in an online development environment. We start with an empty frame spec to see what gets generated. The output is an empty binary spec class, as well as a commented out binary spec controller class that derives from it. This controller class is where we'll put our working action code. This approach enables us to regenerate the base class from the original frame spec without destroying our actions. Now we insert the interface block with the start and change interface methods. As previously discussed, these methods simply create a frame event and send it to the current state, which is tracked in a special state member variable. Taking a look at the frame event class, we can see that it is very simple. Its constructor takes a message and a parameters object and initializes its own equivalent member variables with them, as well as initializing a return member variable, which is not used here but will be discussed in later videos. Now we add our machine block and start state to the spec. By adding our first state to the spec, the FramePiler generates an init method that initializes the special state member variable to the first state in the machine block, which in our case is named start. The start state accepts a frame event and inspects it to see if the message is the special frame start token. If so, the transition statement will be called and pass the reference to the next state to transition into. We now add the 0 and 1 states and see that each has an enter event handler that logs entry into the state, as well as a change event handler that performs the transition to the other state. The major difference between them is that the cycle count is increased when going from state 1 back to state 0. We now add our actions block containing the log method. As we can see, the method simply raises an exception if called, and is designed to be overridden by a controller subclass. Finally, we add the domain block with the cycle count member variable. Unusually, Python requires this member variable to be instantiated during initialization, whereas most other languages allow them to be declared at the bottom of the class. We are at last ready to create a functioning program harnessing frame-generated code. We will use an online development environment called Online GDB, which supports a number of different languages, one of which is Python. We begin by copying the frame event class from a skeleton program which is available on GitHub and is linked below in the show notes. Next, we copy and paste the FramePiler generated classes, uncomment the controller stub, and add code to log the message and number of cycles. As a final step, we copy the boilerplate main sections of the sample skeleton Python code and modify it to drive our controller. We will now write the driver for our frame controller, which will simply call the start method followed by a number of calls to the change method. This interaction will drive the controller to initialize and then start cycling between 0 and 1. With every cycle, the cycle count will be incremented, and with each entry to a state, the status of the machine will be logged and sent to the console. It's showtime. And at last, we now have a functioning state machine using frame notation. I hope you have enjoyed this quick introduction to Frame and are curious to learn more. If so, please check out what's happening on framelang.org, as well as consider joining the communities on Reddit and Discord. There is so much more to explore. Thank you.